Principles of Operating Systems, Chapter 6. Replacement policy has to decide where in the cache a copy of a particular entry would go. If our replacement policy can choose any location in cache to hold a copy of any location in main memory, then it's called fully associative. And the other extreme, if each entry in main memory can go in just one place in the cache, then it's direct mapped. Many of the caches are in between, a compromise, where each entry can go any of several, a fixed number of places in cache. If they can be put in any of n places in cache, it's described as an n-way set associative cache. And an AMD Athlon is two-way set associative. Any location in main memory can be cached in either of two locations in level 1 cache. Choosing the right value of associativity involves a trade-off. If you have several places where the policy says a location can be mapped, then you have to check all of those places to see whether it is in fact in one of them. And checking more places takes more resources and more time. On the other hand, more associativity gives fewer misses, and so less time reading data into cache. General guideline is very roughly that doubling associativity from direct to two-way, from two-way to four-way, has about the same effect on raising the hit rate as doubling the cache size. Increasing associativity more than 4 doesn't really improve the hit rate as much. Higher associativities higher than 4 generally is done for other reasons than improving the hit rate. In order of worst and simplest at worst performance to better but more complicated. Direct mapped, two-way set associative, two-way skewed associative, four-way set associative, 8-way set associative, 12-way set associative, fully associative. With direct map, each location can only go in one location in cache. Direct map then could be called one-way associative cache. A direct map cache doesn't really have a replacement policy as such, since there isn't any replacement policy when the cache entry comes to swap in and out. There is no choice as to where the RAM location gets mapped. If two locations are map to the same entry, then one will move the other out, and then they will swap back and forth. Simpler, a direct map cache needs to be larger than an associative cache in order to get more comparable performance. Further, it's more unpredictable. If X is a block number in cache and Y is a block number in memory, N is the number of blocks in cache, then mapping can be done with the X assigned Y mod N. If each location in main memory can be cached in either of two locations, then the question is, which of the two? The simplest and most commonly used scheme, shown over here, is to use the least significant bits of memory location's index as the index for the cache memory, and to have two entries for each index. One benefit of this is that the tags stored for the cache don't have to include the whole main memory address, just the least significant bit. Since the cache tags have fewer bits, they require fewer transistors. They take less space on the circuit boards. They take less space on the chip. And they can be read and compared faster. LRU is especially simple using this because only one bit needs to be stored for each pair. Speculative execution is an optimization technique where the computer performs some tasks that might, in fact, not be needed. It does the work before it knows whether the results are going to be needed in order to prevent a later delay that would be incurred if the work turns out to be needed. If it turns out it wasn't needed, it just undoes any changes made by the speculative process and goes on. Direct mapped cache allows relatively simple and fast speculative execution. Once an address has been computed, the cache index might have a copy of that location as known. That cache entry can be read and the processor can continue working with that data before it finishes checking that the tag actually matches the requested address. The idea of having the processor use the cache data before the tag match completes can be applied to associative caches as well. A subset of the tag, called a hint, can be used to pick one of the possible cache entries mapping to the requested address. The entry selected by the hint can be used in parallel with the checking of the full tag. This technique works best in the context of address translation. A cache miss is a failed attempt to read from or write to data in the cache. That a cache miss requires a main memory access, and the reason for using cache to begin with is fast access. There are three kinds of cache misses: reading an instruction and not finding it in cache, a data read miss, and a data write miss. Cache read misses from an instruction cache generally cause the longest delays because the processor has to wait until you get the instruction from main memory in order to continue. Cache read misses from a data cache are not quite as serious. They don't cause quite as long as a delay because the instructions are not dependent on the cache, that are not dependent on the cache read, can be issued in continued execution until the data comes in from main memory and the dependent instructions then can resume. Cache write misses to a data cache generally cause the shortest delay because that write can be queued. There are not too many limitations on the execution of subsequent instructions, so the processor can continue, at least until the queue is full. A disk cache is a mechanism for improving efficiency of access to secondary storage. Disk cache holds data that has been recently read in from disk and also holds adjacent areas that are likely to be accessed next, but it holds it in a storage area that's easily more efficiently accessed than direct secondary storage, direct disk access. Most hard disks now have disk caches built in. When it's built into the hard disk, it's called a disk buffer. You can also do it in RAM, a section of primary storage. And if you do it in RAM, it's called a soft disk cache, or sometimes a page cache. Disk cache improves the processing, enables faster processing of I/O between hard disk, primary storage, and computing components. Once the process modifies the contents of a page so that it no longer matches the content of what's actually in secondary storage on the disk, that page then will have to be flushed out to disk, written to disk, before that section of the cache can be reused by other data. A dynamic linker is a part of the operating system that loads external shared libraries into the running process and binds them dynamically into the process. It's called dynamic linking or late linking. Since you can use the same instance of the library process for multiple processes that economizes memory use.